Now, in the first part of Lecture 8, we will be concerned with the electrical properties of membranes and of the cytosol of axons. Signals coming from, for example, your foot are traveling by electrical means through your body into the brain. Hence, the cells that are responsible for those, the neurons, have a very long stretch, basically going through your spinal cord, which is called the axon. So the axon is typically in the order of a millimeter thick cable, and it has a length of the body size through which electrical signals will travel. If you measure the electrical signals that are traveling through the axon, they are characterized by a change in the membrane potential from the resting potential of minus 60 millivolt going to a positive value of plus 45 millivolts. And this signal is stable along the whole axon. Now, the experiment to prove that is that you stick very thin needles into the axon at various positions, here the red, green and blue, and you measure the voltage that is going across the membrane at that particular location. And you will see that the membrane potential changes at V1 at an earlier time as compared to V2 and compared to V3. So let's cook up an electrical equivalent circuit in an attempt to understand the signal transduction through the membrane. Well, the first ingredient is that the membrane has a particular resistance. So if we have a phospholipid membrane and we apply a voltage across, there will be also some current flowing. So in terms of electricity, this is equal to just a membrane or a resistance, where the resistance scales with the area of the surface of the neuron. So the membrane resistance R is equal to rho divided by A, where rho is the specific resistance measured in ohms per meter or per square centimeter. So typical values are there's a very high resistance for just pure membranes in the order of 10 to the 8 ohm per square centimeter, whereas for cells, and you know that there is, for example, the sodium-potassium pump that makes the membrane more leaky, the membrane resistance is in the order of between 1 and 10 to the power 4 ohm per square centimeter. Now, for a typical cell of a typical size of 10 micron diameter, and we assume just a spherical cell, the membrane resistance is in the order of 30 mega ohms. Now, on top, the membrane also will work as a capacitance. Well, we know if we apply a voltage, the potassium ions will accumulate on one side, whereas the chlorine ions will accumulate on the other side. Hence, we have here a charge separation at a distance of d, which is equivalent of being a capacitor. So the membrane also has a capacitance characterized by the capacitance is equal to the specific capacitance, small c, times the area of the membrane. Now, the specific capacitance is just given by the permeativity of the substance divided by the distance between the two poles. Now, this last equation you should still recall from electrostatics. Now, for cells, the typical permeativity is in the order of 2. The thickness of the membrane is 5 nanometer. Hence, the specific capacitance is 0.4 microfarad per square centimeter. Again, for a typical cell of 10 micron diameter, the capacitance is in the order of 1 picofarad. Now, hence the membrane we can visualize as a parallel connection of a resistance and a capacitance from one side to the other side of a voltage source. So a typical membrane circuit would be like this. We apply an outside voltage V, there's a switch, then there's a membrane characterized by a parallel R with a parallel C, and we can measure a current. Now, applying Kirchhoff's rules, meaning that the total current has to be the sum of the current through the resistor plus the current through the capacitor, which we can determine by the electrical voltage U. So the current through the resistor is U divided by R, and the current through the capacitor is the capacitance times the time derivative of the voltage. Now that leads to a differential equation reading that du dt is equal to 1 divided by RC IR minus U, which we simply can solve, leading to that so if we close the switch, the voltage will increase to a maximum voltage of U infinity times 1 minus exponent t divided by tau, where tau is the characteristic time scale, is given by 1 divided by RC. Now, typical for a cell, this RC time is in the order of 3 microseconds. Hence, if I apply a voltage jump to a membrane, within 3 microseconds, the membrane voltage will change.